Okay, so then a final video for this section, which I just want to mention non-metric and non-Euclidean multidimensional scaling methods. So our focus throughout has been on classical MDS. So just to remind you, classical MDS was to do with, well, all MDS to do with solving a problem like this. We're finding a bunch of points in R dimensions that minimize some objective, where the objective is normally in terms of the distance between the points you found being close in some way to the distance matrix you were provided with. Now, classical MDS assumes these distances are Euclidean, and it uses this cost function of squared errors. But in general, we can do more complicated things, and that might find more interesting structure. So we don't have to use squared errors here. We don't have to use Euclidean distances. So I don't want to go into the details of any methods. Okay, I've named some methods here that you can easily try out. Okay, well, instead of using this CMD scale command, you can just substitute them with one of these commands, and it'll do some form of non-classical MDS. What I have done is given you a link here for this amazing website that implements a whole bunch of these methods for the MNIST data. So it's got some of the plots that we've had. So it's got the PCA plot I gave you in the notes here, where it's projected these the first two principal component scores, but it's done a really nice visualization here where when you hover over the points, you can see what image it is. So it's well worth reading and looking at. So then it gives us various optimization-based dimension reduction approaches, starting with MDS. So this is a version of results we've had that allows you to zoom in and look at all the different points and see how they're clustered. Okay, so this is a form of classical metric MDS. Another form of MDS is something called Salmon's mapping. Now, in Salmon mapping, instead of using the squared errors, we divide here by the distances as well. And the idea of dividing by the distances here is to try and preserve small distances. Yeah, the squared error that we have in classical MDS makes sure that the big distances are about right. The Salmon's mapping, it tries to preserve small distances. By dividing by here, you lessen the impact of the square here, and you're trying to make small distances preserved. So let's have a look at that. Okay, that looks slightly nicer to me, although it's still not great, but you can see it's given a slightly different clustering here. Okay, but it's not really that different to what we got before. Now, there's a whole world of methods out there. You know, there's people who, the whole community is researching these things. And a lot of the methods are these graph-based methods. And I don't want to talk about these at all. I just want to show the kind of thing they can do. So here you try and build a graph structure linking the different elements. Okay. If I zoom out a little bit here, you can see this is looking like it's done really well here. You've got all these purple points joined together, the 8s, you've got the 3s joined together, you've got the 6s nicely clustered together, the 0s. Remember, this is not a clustering algorithm. The algorithms are not given the digit labels here. They're just looking for low dimensional representations. So it's done impressively well, I think. Perhaps one of the most successful methods is this TSNE approach. Okay, and again, I don't want to talk about the details, but just have a play around with this. Okay. So here it clusters the points, and you can begin to see how quickly it finds the relevant clusters. Okay, so it's an optimization approach, so this will just keep ticking away, moving the points around. Okay, but you can see it does well. Okay, I think they've got plots somewhere. Yes, so there's a plot here where they've let it run for a long time, so this is actually optimized, and you can see it really clearly here, pulled apart the different groups in the data. Okay, so we can do amazing things with dimension reduction now. There's some amazing methods out there for you to play around with, and these all have implementations in R, so you can go and try them for yourselves if you want. Okay, it's also done them in 3 dimensions. We talked about 2-dimensional representations, but we can, of course, plot in 3 dimensions. So on the example sheet, I'll ask you to do that, not with these fancy graph-based methods, but with MDS. Okay, so I think they've got the MDS results here for MNIST, and you can see that works a bit better here. It seems to have pulled the clusters apart much more successfully in 3 dimensions than in 2 dimensions, which is not a surprise particularly. Okay, but you can zoom in and have a look around at these things. It's pretty cool. Okay, and they got the various other results. Have a look. If it takes your interest, play around with them. Okay, I'm not going to set any exam questions on these things. Our focus has been on classical MDS. Okay, that is what we're interested in here. Okay, and that's the end of the multidimensional scaling chapter.